Electric potential energy. Potential energy in general is when you're in a position where there's a force that would like to do work on you if it was allowed to. So for example, with gravitational potential energy, if you're at the top of the hill, the force of gravity would like to do work on you. So if you just get a little push here, then you can roll down the hill, and that force of gravity is able to do that work on you that it wants to do. Similarly, electrical potential energy is when you're in a position where an electrical potential force would like to do work on you. However, because with charges, there are positive and negative charges, we also have to consider that there's electrical potential energy that can be negative, that can also be when you're in a position where that force has done work on you, and as a result, you've lost energy to some other form. So first of all, if we imagine two positive charges that are close together, and let's just say for some reason that this one has a fixed position, then this would be a situation where both charges, but this charge has electrical potential energy. There's a repulsive force between these two charges that would like to do work on that secondary charge. And if it was allowed to, if the position became unfixed for this, then this particle would fly off in this direction, gaining kinetic energy and going to a state of lower electrical potential energy. So here it has electrical potential energy. We have to be a little careful with electrical potential energy. We've just in the past called E the electric field, so that's usually what we use for energy. So for electrical potential energy, we'll use the letter U. So this electrical potential energy is in this situation, and if this force is allowed to act, it's allowed to do work on this particle, and it flies away, and here it has some speed v, then that electrical potential energy is being converted to kinetic energy, just like a ball rolling down a hill. Alternatively, though, we have a different situation with electrical charges that we don't have with gravity. We could have a positive and a negative, in which case this charge has been drawn in through a force of attraction. This electrical potential energy, so this one would have been a positive one, that's my positive example. This electrical potential energy would be negative because as it got drawn in, this source of attraction would have allowed energy to be taken out of this, or it's going almost like a ball rolling into a hole. Energy has been available to other forms, like maybe kinetic energy or something like that, as this charge gets drawn into this attraction. In either case, unlike what we did for gravitational potential energy at first, but I guess sort of similar to what we did eventually, the reference point for zero potential energy becomes sort of obvious when we imagine these charges interacting, where we have repulsive going to a positive and attractive going to a negative. Potential energy zero is set when the distance between the two charges that we consider to be interacting is infinite, or they are very, very, very far away from each other. So if this is potential energy, then this would be more negative because they're closer together. So how do we get to zero? Well, we get them really far apart. Can't even see that other charge anymore. Okay, so the formula for this, similar to the universal gravitational potential energy, is the constant proportional to one of the charges, proportional to the other charge. And then unlike, you've got to be careful with this one because it looks very similar to the force formula, but it's just a little bit different. Unlike the force formula, we divide by the radius, not the radius squared. Here, because like charges repel and unlike charges attract, if we're careful with our signs, we will get positive energy when we're in a repulsive situation or we're at a high potential energy, and we'll get negative if we have an attraction or we're in a situation where a particle has been drawn in or they're bound together. And as r goes to infinity, u goes to zero. So this works perfectly also for when the particles get very apart, the zero reference point energy that we want naturally occurs. So let's just do a really simple calculation here. Let's imagine that we have a proton and electron and we have them 0.529 nanometers away from each other. So a proton, the charge on a proton is 1.6 times 10 to the negative 19 coulombs. The charge on an electron is negative 1.6 times 10 to the negative 19 coulombs, the elementary charge. And the distance between them would be 0.529 nanometers, or nanometers is times 10 to the negative 9, so 0.529 times 10 to the negative 9 meters. Potential energy then, KQQ over R, 9 times 10 to the 9, times 10 to the negative 19. Because again, we're using the scalar equation, we're not going to interpret our direction like we did in previous examples using the law of electrostatics, but instead we'll interpret our sign by including the sign properly in the equation here. So there we go. Okay. 9 exponent 9. So as an idea for a magnitude of potential energies associated with just proton-electron interaction, I got 4.36 times 10 to the negative 18 joules, which seems like a very low number because we got the 10 to the negative 18 here, but we have to remember that these particles have very, very small masses as well. So this is a very significant amount of energy considering the actual mass of these things, but also considering in a typical piece of matter how many of these things there would be. I just want to hit that in the calculator one more time, make sure I didn't mess it up. Oh, I did it again and I got a different answer. I better double check that one more time. 9 exponent 9 times 1.6 exponent negative 19 squared divided by 0.529 exponent negative 9. Oh, yeah, it should have been negative 19. Not negative 18. So I just hit a wrong button there in my calculator. That's why when I have a big calculation like this, I typically will hit it twice so that I make sure that I didn't make a mistake like I did here. And so I caught that. Anyway, also don't forget I had a positive and a negative here, so this is negative. And what that negative means is that this is an attractive force that brought these two things together. That means this much energy would have been available to other forms, say like the kinetic energy of the electron as it got drawn towards the proton. Or another way to look at this is how much energy you would have to add to get the electron back to zero energy. Or what we mean by that is to get the electron away from the proton to separate the charges. This is a little bit like saying that a ball has fallen in a hole, and so that's how much energy you would have to pay to get the ball back out of the hole. The Earth attracted the ball in, so that's an attraction, so you have to pay energy to pull it back out. And sometimes, because of that, this is called an electrical potential well. And that's sort of referring to like a water well, which is a hole in the ground that you have to pay energy to get stuff out of it. And that's like this electron and proton's attraction, or trying to keep them together. So you're going to have to pay energy to separate them. So that is electrical potential energy.